Hello, welcome to this new lecture of the course Transportation Network Analysis. So, today we will be starting a new topic which is called traffic assignment. So, this problem is quite different from the kind of problems that we have seen until now, because this will be a continuous optimization problem, whereas we have seen discrete optimization problems until now where we had to select decisions among a finite set of solutions. So, we will be learning a lot of new concepts as we will move along, and let us now start this traffic assignment problem. So, to start with, we will be solving this problem on road networks. So, we will be representing these road networks by directed graphs. So, just to remind, directed graphs involve links or edges that have directions. So, this is an typical example of a directed graph. So, here a node can represent an origin of a trip. For example, suppose if node A is the origin of a trip, then node C is suppose the destination of a trip, and we have an intersection here at node B. So, here a link can represent a one-way street. Okay, so here we are dealing with directed edges, so every link has a direction, and therefore a two-way street will be represented by two opposite direction links here. So, here there are streets in both the directions between A and B. So, there is one edge which is going from A to B and the other is going from B to A. So, transit networks can also be represented by graphs, and they can be analyzed in a similar manner as road networks, but we will not be discussing the assignment on transit networks because of the limited time that we have, and we will be just focusing on traffic assignment for road networks. But once you have a foundation of the concept that you learn here, it is not difficult to learn the concepts of assignment and transit networks. So, one important concept that is required to solve the traffic assignment problem is of the origin destination matrix. It is also called in short OD matrix. So, this represents the travel demand. Okay, so it represents, for example, the number of people who want to go from one place to another. So, let us take a look at this example here. Suppose two people want to travel from node 1 to node 2. Okay. So, this is the OD matrix or the origin destination matrix for this kind of movement. So, here the entry ij of this matrix represents the number of people who want to travel from node I to node j. So, the index I is going along the rows here, and the index j is going along the columns here. So, you can see that only this one entry which is in the first row and the second column is positive. So, that is saying that two people want to travel from node 1 to node 2 here, and everywhere else the flow is 0. Okay. So, this is what it is saying. So, two travelers want to travel from node 1 to node 2, and here we will be also making an assumption that every person or every traveler will be going in a single vehicle. So, there is when we say that the number of people who want to travel from place A to place B is suppose x, so we are kind of assuming that x number of vehicles are also required for that purpose. Okay. We will be assuming that the origin destination matrix is fixed with time. What does it mean? That we are not considering the variation of this travel demand as time progresses. Okay. Although ideally in the real world that is taken into account in more complex extensions of traffic assignment, which are called dynamic traffic assignment. We will be focusing on the static traffic assignment here. So, another important concept which is required in the traffic assignment problem is of the link performance function. It is also called sometimes the link travel time function. So, this represents the variation of travel time of link as a function of the flows that pass through it. Okay, so this is an example of a link performance function. On the x axis we have the link flow, on the y axis we have the link travel time. So, you can see that as the flow is increasing through this link, the travel time is also increasing. Okay. So, this is saying the same thing. A typical link performance function is a monotonically increasing function with respect to the link flow, and that also matches with the intuition that as the flow through a link increases, the travel time should increase. That is, as more and more congestion increases through a link, the travel time should increase. So, here in this figure we have this concept of free flow travel time. So this is the travel time at zero flow. Okay, so this value here. So here there is no flow, zero flow. So whatever travel time you get at that flow value, this is called the free flow travel time. Physically, it means that if suppose the road is empty, then how much time it will take for a vehicle to travel, given that the vehicle is suppose traveling with the speed limit that is set for that road. Okay. Then there is another concept of capacity. So it is the maximum flow which is allowed through a link. Okay. So here you can see that this is the limit of the maximum flow that is allowed through this link. So this is the capacity. So like the origin destination metrics, link performance functions are also assumed to be fixed with time. Okay, so we'll be assuming that this link performance function for every link will stay the same. There will be no change there. So when the origin destination matrix and the link performance functions are assumed to be fixed with time, they come in the category of static traffic assignment. Okay. And the target of the traffic assignment problem is to find flows on all the links given the road network, the link performance functions and the origin destination matrix. Okay. So we want to determine how much flow will take place through different links, given that we know what road network we have, how does the travel time change on different links as the link performance functions are given, and how many people want to travel from a place A to place B. Okay, so this is given in the OD matrix that is provided to us. Okay. Now, as you might think that the flow assignment in different links need not be a single solution, it will depend upon lot of factors. It will depend upon what are the priorities of people, that is what is the behavior of people while they are traveling on the road. For example, if everyone is interested in going to the path that offers the shortest travel time, so then the link flows that we might observe might not be the same as compared to, for example, if people want to travel on the roads which are most familiar to them. Okay, so that's why we require one more thing, that is what assumptions that we are making on the behavior of people while they are traveling. Okay. So let us understand this traffic assignment problem through this case here. So suppose we have two nodes A and B here, they are connected by two paths, path 1 and path 2. Let us assume that path 1 has the shortest free flow travel time. Okay. Now one assumption that we are making is that each traveler is trying to minimize his or her travel time while traveling from A to B. Okay. Now if all the travelers take path 1, the travel time on this path might increase to a point where it is no longer the minimum travel time path. Okay. So it can happen that although path 1 offers the shortest free flow travel time, but that is the shortest free flow travel time, that is when there is no flow through that link. But if suppose 100 people want to travel from A to B, and if all 100 people decide to take the path 1, then the travel time on that path will no longer be equal to the free flow travel time. It will only increase, as we have seen in the link performance function, because the travel time increases with the flow here. Okay. So then whatever travel time we will be observing might no longer be shorter than the free flow travel time on path 2, because since no one is traveling on path 2, so there the travel time is equal to the free flow travel time. Okay. So that's why this situation might not be stable, and therefore some travelers might want to shift to path 2, okay, so that they minimize their own travel time. However, if everyone suppose decides to shift to path 2, then that can also get congested. Okay. And this back and forth transfer of flow between these two paths can keep going until we reach a stable situation where no traveler can improve his or her travel time by unilaterally changing routes. Okay. This condition is called the user equilibrium condition. So in this condition, there is no incentive for any traveler to change his decision on what route he or she is choosing, given that no one else decides to change their decision. That is what we mean by unilaterally changing route. So no traveler has an incentive to change his decision of route. That point or that condition is called the user equilibrium condition. So then that's a stable condition. So some people are supposed then traveling from path 1, some people are traveling to path 2. The people traveling on path 1 don't want to shift to path 2, those traveling on path 2 don't want to shift to path 1. Okay. So let us state the assumptions that we make in the user equilibrium condition more formally here. So first assumption is that on the behavior of people, that is each traveler is minimizing his or her own travel time. We are also assuming that each traveler has full information of the travel time on each route. Okay, so they know how the link performance functions vary. Then we are also assuming that each traveler is rational, that is he or she takes the best decision. So they will always try to take that path which will minimize their travel time. Okay, they will never try to adjust a little bit so that they get slightly more travel time, but others are able to minimize their own travel time. And each traveler is identical in behavior. This assumption that each traveler is identical in behavior is useful because that allows us to make this assumption that instead of these different people who are traveling from place A to place B, we can think of them as a flow which is going from A to B. And here we will be assuming that the flow is allowed to take continuous values. Okay. So what it means is that suppose total of 1000 people want to travel from a place A to place B and there are two paths. So solutions such as 500.5 people traveling on first path and 499.5 people traveling on the other path, that kind of solutions are allowed. Okay, although these solutions are definitely not realistic because the people are discrete, so we cannot consider them as fractions, but they are very well useful in doing the optimization, because when we make that assumption, then we go into the realm of continuous optimization, and then we can use a lot of techniques such as differentiation and so on. Okay, double differentiation and those kind of things. So that makes the optimization much more solvable. And when the flow between different places is large, for example, when we are talking thousands, hundreds, millions of people going from A to B, so then 500.5 versus 500, that solution is more or less the same. So that difference of fraction does not make much difference. Okay. Now, in the version of user equilibrium that we will be currently focusing, we will be making these assumptions here. But then there are many extensions of the user equilibrium problem in the literature where one or more of these above assumptions is relaxed. Okay. And the question might come is that why are we not directly going to those extensions which are more realistic than this one? Because we want to follow this approach that we first try to solve a simpler problem, gets insight from there, and then only it's better to solve a more complex problem, because if you are not able to solve a simpler problem, it is not possible that we will be able to solve a problem which is even a generalization of that or more complex than that. Okay. Okay, so let us see an example to better understand this user equilibrium problem. Suppose we have a two-link network here which is shown. We have the travel time functions which are plotted here for both the two links here. So this is the travel time function of the first link, this is the travel time function of the second link here. This A is the free flow travel time on the second link, B is the free flow travel time on the first link. Okay, and here you can see that we have drawn a horizontal dash bar from A, and then wherever it strikes the link performance function of the first link, we have dropped a vertical dash here. So this point, this value is called Q dash. Okay, so this is that flow on link 1 at which the travel time on link 1 becomes equal to the free flow travel time on link 2. Okay, what is the free flow travel time on link 2? It is equal to A. So since the travel time function of link 2 is always above than the travel time function of link 1, so when the flow on link 1 is equal to Q dash, the travel time that is experienced on that link is equal to the free flow travel time that is experienced on link 2, which is equal to A. Okay, so let us consider two cases here. First is that suppose the travel demand from O to D is very small, that is the demand is less than Q dash. Then all the travelers will choose link 1. Why is that? That is because when the flow on link 1 is less than Q dash, travel time on link 1 is always less than A. Okay, which is the free flow travel time of link 2. So if the total flow that is taking from O to D is less than q dash, so then if everyone stays on link 1, they will not be experiencing travel time which is greater than A, because they will always be lying in this region here somewhere, and it will never exceed A, which is the free flow travel time on link 2. Okay, so you will be always experiencing at least travel time of link A on link 2. Okay, because that is the free flow travel time even if there is no flow through that. Okay, so if the total flow from O to D is equal to q dash, then everyone should choose link 1 only. Okay, and I would like to emphasize one more thing, is that while we are doing this discussion of static traffic assignment, the reference book that people can refer to is called Urban Transportation Networks by Joseph Sheffy. So that book is available publicly online. So I'll be following very closely from that book because it's a very classical book. Okay. Okay. So here in this case we see that all the demand flows to link 1 and there is 0 flow on link 2. Okay. And you should know that this case satisfies the user equilibrium condition. Why is that? Because now there is no incentive for any traveler which is on link 1 to shift to link 2, because they are anyway experiencing travel time which is less than or equal to A, the free flow travel time on link 2, and therefore if you shift to link 2, you will only get a travel time which is higher than A. Okay, so there is no point of doing that. So this satisfies the user equilibrium condition. Okay, let us now go to another case where now the demand of people who want to go from O to D is greater than q dash. Okay, now here the equilibrium can only be maintained if there is a flow on both the links and the travel time on both the links is equal. Okay, so here you can see that now you cannot afford that everyone stays on link 1, because this is that q dash. Okay, so if the total flow from O to D, that is the demand, is greater than q dash, so then if you keep suppose all the flow on this link only, okay, then some people or some travelers might want to shift to link 2 because this point is having less travel time, that is the free flow travel time of link 2 is smaller than that. So that's why in this situation the only possibility that is there is that both the links will have to have flow passing through them. Okay, and in order for the equilibrium condition to be maintained, the travel time on both the links have to be equal. Okay, only in that situation there is no incentive for any traveler to change. Okay, so that will tell you that there will be unique solution to this problem, because only one case will satisfy that this x1 plus x2 is equal to the total demand. Suppose the total demand is q. Okay, so we have to ensure two things. First, the total demand x1 plus x2 has to be equal to q, which is the travel demand that is given, and the travel time t2 x2 has to be equal to t1 x1. So only this case suppose will satisfy this. Okay, because in any other case some flow will shift towards the lower time link here. Okay, and just to again remind you, we are assuming the traffic flow to be continuous, so we allow traffic flows to take fraction values. So let us now generalize the operational definition of user equilibrium. For each OD pair at user equilibrium, the travel time on all the used paths is equal and is less than or equal to the travel time on any unused path. What does that mean? Now that we have taken a look at both of these two cases, let us go through these one by one. So in the first case, when the total demand was less than q dash, so then all the flow was taking place through link 1 only. So link 1 was only the used path, the other link 2 was the unused path. Okay, so there the travel time on the used path, that is link 1, was less than or equal to the travel time on the unused path, that is link 2. Okay, and in this case both the links are getting used, that is both the links have positive flow, so both of these two paths alternatively are getting used here. Okay, so that's why both of the paths are used and they have equal travel time. Okay, if suppose there were 3 paths that we had, or 3 links in this example, and suppose the 2 of them were getting used, that is they had positive flow and the one of them didn't have, so in that case the 2 paths that have positive flow, so there the travel time will be equal, but the travel time experienced on then will be less than or equal to the travel time that is experienced on the third path. Okay, so let us take a look at this through an example here. So suppose we have this network here, origin to destination, people have to go, there are 2 links through that. And here in these kind of examples we can use link and path interchangeably, because a path only consists of one link here. So path 1 just has link 1 and path 2 only has link 2, and these two paths are not overlapping with each other. Okay, suppose these are the travel time functions that are given to us. Okay, suppose the total demand is equal to 0.5. Okay, now this 0.5 value has only been taken for the example purpose. In the real world these demand values will be in thousands and so on. Okay, so this is just for the illustration, because we can take any value here. Now if all the flow is assigned to link 2, then the travel time that will be experienced on link 2 will be equal to 1.25. Okay, now that is less than 2, which is the free flow travel time on link 1, because if you put x1 equal to 0 here, you will get t1 equal to 2. Okay, so it's saying that 2 units is the free flow travel time of link 1, and therefore the user equilibrium solution is to assign all the flow to link 2, that is set x1 equal to 0 and set x2 equal to 0.5. Okay, because when we do that, the travel time that is experienced on link 2 is 1.25, which is less than the free flow travel time on link 1. Okay, so then there is no point for people to choose link 1. Okay, now let us take a look at another example here. Now suppose the demand is equal to 2 here. Okay, now if all the flow is assigned to link 2, then the travel time that will be experienced on this link will be equal to 5 units, because the travel time expression for link 2 was 1 plus the flow of that link squared. Okay, so it is equal to 5, which is greater than 2. In this case both the links will have to be used, because if you assign everyone to link 2, then the travel time on that will be greater than the travel time that will be experienced on link 1 if there is 0 flow. So then it makes sense to use both the links here. So therefore the user equilibrium solution will be obtained by having positive flow in both the cases, and for this case the flow should be such that the travel time on both the links is equal. Okay, so this is the first equation that we will be getting, that we equate the travel times on both the links here. And the other equation that we have is of the flow conservation, that the total flow has to sum to equal to 2. Okay, so if you solve these two equations, so we have two variables and two equations, so the solution we will be getting is this here. Okay, so with this we will be ending the discussion for this lecture. Thank you.